Alright, so for this section, we're going to go ahead and cover 7.3, right angle trigonometry. In this section, we're going to go ahead and finally introduce our trig functions. In particular, we're going to talk about them in respect to a right triangle. So whenever I talk about a right triangle, just so that we're very clear about it, a right triangle refers to a triangle that contains a right angle. So, for example, I have this picture right here. So here we clearly have a right triangle. It has a right angle as indicated by the square here on the bottom left. So in a triangle, we clearly have three angles. We have, in this case, we have our right angle on the bottom right, and then we have the angle here on the bottom left, and then this angle on the top. So what I'm going to do is that I'm going to focus on either one of these two angles, either this top angle or this angle on the bottom left. It doesn't really matter which one I focus on as long as I'm consistent. Let's say I focus on this bottom left angle, and let's call it theta. I'm going to give it some name. So when I'm working on this triangle, one thing that I may be interested in is naming the sides of my triangle. Clearly I have three sides. So the first side I want to talk about is the hypotenuse. The hypotenuse, first off, will be the side that's across from my right angle. So we see here we have our hypotenuse, and it's across from the right angle. Another way that you can think about it is that the hypotenuse is always the longest side of the three. So we have our hypotenuse. The next side I want to talk about is the opposite. So this is the side that is opposite to my angle of choice. So it's opposite to theta. And then the third side, we're going to call it the adjacent. So the adjacent means next to. So this is the side that is next to theta that is not the hypotenuse. So I have these three sides. And one thing I want to just clarify as well. So these sides are labeled based off this angle on the bottom left. If, on the other hand, I labeled and fixed the angle on the top, then my hypotenuse is the same. That's not going to change. But my opposite and adjacent are going to swap sides. Opposite is going to be the side on the bottom, and adjacent will be the side on the right. So my opposite and adjacent, those depend on which angle am I focused on. So this is what we have as our right triangle, and how we label the three sides of my right triangle. And this is going to be important for our next couple of definitions. So now that we have the sides of our triangle labeled, I can now figure out how do we define our 6 trigonometric functions. So actually I'm going to start off with the first three, because those are going to be the ones that are more important, or rather than more important, the more common ones. So the first trig function I'll introduce is sine of theta. This is S-I-N-E. That's how it's spelled, of theta. So sine of theta. This is the opposite side length over the hypotenuse side length. So if I know what value the opposite is, and I know what the value of the hypotenuse is, then I know what sine of theta should be equal to. Next, I have cosine of theta. This is the length of the adjacent side divided by the length of the hypotenuse. And then I have tangent. Tangent is the opposite length divided by the adjacent length. So these are the first three trig functions I wanted to introduce. And these are the more common ones that you've probably seen before. And one way that a lot of students try to remember this formula, if you want to call it that, is through the phrase SOHCAHTOA, for sine is opposite over hypotenuse for so. Ka is cosine is adjacent over hypotenuse. Toa is tangent is opposite over adjacent. This is a common thing. You may have heard this before. If you haven't, it's a very quick way that people remember what is sine, cosine, and tangent equal to, respectively. So this is three of the trig functions. But what about the other three? So the first one I'll introduce from the other three is the cosecant of theta. Cosecant of theta is the hypotenuse divided by the opposite. Next is the secant function, secant of theta. This is the hypotenuse over adjacent. And then cotangent. This is adjacent over opposite. So there's a reason why I formatted these 6 trig functions in this particular order. So on the left I have sine, cosine, tangent. And then on the right I have cosecant, secant, cotangent. I want you to notice something about each row. For the first row, sine and cosecant. Sine is opposite over hypotenuse. Cosecant is hypotenuse over opposite. Second row, we have adjacent over hypotenuse, and then hypotenuse over adjacent. So what are we noticing here? Well, if I compare the left side to the right side, it just looks like I flipped my fraction. Opposite hypotenuse, hypotenuse opposite, so on and so on. So this is the common way that a lot of books tend to write these 6 trig functions. The cosecant, secant, and cotangent functions are the same values, just reversed. One other thing that I want to point out here, well, 2 things. First one being that these definitions, hypotenuse, opposite, adjacent, only work if I have a right triangle. If I do not have a right triangle, I can't use these definitions anymore. We'll actually use a different definition that we'll learn later on. Secondly, another thing that students often mix up is that here we have sine and cosecant are reverses of each other, and cosine and secant are reverses of each other. A common mistake I see is that a lot of students mix up, say, sine and secant are reverses, and cosine and cosecant are reverses, because they think S and S, C and C, but make sure that we have these in the proper order. So now we have our 6 trig functions. Let's go ahead and do an example. Example 1. Given the following right triangle, determine the values of the 6 trig functions at the given angle theta. And I gave you this diagram where I labeled the length of each side and I fixed my angle theta. So everything's going to be labeled in respect or in relation to this angle theta. So the first thing I'll probably go ahead and deal with is I like to label what each of these sides are. Which one's the hypotenuse? Which side's the opposite? Which side is the adjacent? So let's start off with the hypotenuse. The hypotenuse should be the longest side, or in other words, the side that's across from the right angle. So here I have the right angle. The side that's across from it is this 5. So 5 is my hypotenuse. Now what about my opposite and adjacent? Well, my opposite, this refers to the side that's opposite to my angle theta. So here's my angle theta. The opposite end is 4. And then that leaves 3 to be my adjacent side. So I labeled my opposite, adjacent, and hypotenuse. After I labeled my triangle, I now have enough to find my 6 trig functions that I have here. So this is going to be important for us to remember which one is opposite, hypotenuse, adjacent, hypotenuse, whatever it may be. Let's start with sine. So if you remember from the previous slide, sine is opposite over hypotenuse. Again, you can use the acronym, the little phrase, SOHCAHTOA. So if I take the opposite, I have 4 divided by the hypotenuse, 5. So I should have 4 over 5. And that's already simplified all the way. I can't reduce that any further. So I'm done with sine. Now let's move on to cosine. Cosine should be adjacent over hypotenuse. The adjacent is 3. The hypotenuse is 5. So I should have 3 over 5. Next is tangent. If I think of a SOHCAHTOA again, tangent should be opposite over adjacent. So the opposite is 4. The adjacent is 3. I have 4/3. So I have the first 3 trig function values at this angle theta. And before I move on, one quick thing I want to note is, notice that I have no idea what this angle actually is. It could be 30 degrees, it could be 45 degrees or something. We're not sure yet, but that doesn't matter. All we need are the sides of my triangle. All right, now let's look at cosecant. Remember, cosecant is the opposite of sine, or the flipped version of sine. So sine was opposite over hypotenuse, so cosecant is hypotenuse over opposite. That is at 5 over 4. One other way that you can find this is notice the difference between sine and cosecant. We've pointed this out before, but cosecant is just the flipped version of sine. Using that idea, we should pretty much end up with the same idea for secant and cotangent. So secant should be the flip of cosine, so instead of 3/5, we have 5/3. For cotangent, instead of 4/3, we have 3/4. So generally speaking, if you know the 3 on the left, then you know the 3 on the right. There's going to be one small note, actually, that we're going to see in the next example, where it's not going to look exactly the same as just flipping it, and that often is going to happen whenever we start working with square roots, which we'll end up doing in example 2. But whenever we have these clean numbers, it looks like we can just flip them immediately. Alright, so let's move from here. This example wasn't too bad because I had all 3 sides of my triangle already labeled. But what if I was missing, I don't know, the hypotenuse? What if I was missing the opposite, or if I was missing the adjacent, missing one of them? What can I do from there? Well, in that scenario, we actually have this nice theorem that we call the Pythagorean theorem. So, if I have a right triangle, right being a key word here, where A and B are the legs of my triangle, the legs referring to not the hypotenuse, in this case, this bottom side and this vertical side, and C is the length of the hypotenuse, then we have the equality A squared plus B squared is equal to C squared. This equality should always work out for any right triangle. One small thing I want to also note is that my choice of A and B was completely arbitrary, meaning I could have put let A be this vertical length and B be this bottom length. The most important thing is that C always has to be the hypotenuse, the longest side here. Alright, so this Pythagorean theorem tells me if I only have A and B, I can find C. If I have A and C, I can find B. Or if I have B and C, I can find A. So long story short, if I have 2 sides, I can use this equation to find what the third side is. Alright, so in this, now how can we apply the Pythagorean theorem? This is when we start going into example 2. So again, I have a right triangle, but only 2 sides of my triangle are labeled. I have no idea what this bottom part is yet. But if I want the 6 trig functions, I know I need all 3 sides of my triangle. So we're going to split this up into 2 parts. The first part being I need to figure out what this third side is. After I figure out the third side, I can move on to part 2 where I can figure out what are my 6 trig functions at the given angle theta, where theta is this angle on the top right this time. Alright, so let's start off by figuring out what the third side is. For convenience, let me go ahead and label this triangle a little bit. I can go ahead and say let A be equal to 2, B be this bottom side, and C be the hypotenuse. Again, I want to remind y'all that C always has to be the hypotenuse. For A and B, it didn't really matter which one was which. I could have said B is equal to 2 and I'm trying to find A. The order for that doesn't really matter. The most important part is that C is always my hypotenuse. If you accidentally say A is equal to square root of 29 or B is equal to square root of 29, you're going to start getting some really weird answers that might not make sense. Alright, so since I have a right triangle, I know I can use the Pythagorean theorem. A squared plus B squared is equal to C squared. Well, A is equal to 2 based on how I labeled it. So I have 2 squared I don't know what b is, and that's what I'm trying to figure out. And c is the square root of 29. And remember that we're squaring each one of these. My goal is to figure out what is b. So I should probably clean up this a little bit. Starting on the left, 2 squared. 2 squared is 2 times 2. I get 4. Plus b squared. I can't really do anything with that b squared yet. And on the right, how do I clean this up? Well, remember, a square root and a square are opposite operations, just like how plus and minus are opposite, multiply and divide are opposite. So using that idea, if I square a square root, we can think that they cancel each other out, leaving me with whatever was inside, 29. So I have 4 plus b squared is equal to 29. Now I need to get b alone. First step would be subtracting 4 from the left and right. On the left, 4 minus 4, I get 0, leaving me with b squared on the left. And then 29 minus 4, I get, well, 25. So I have b squared is equal to 25. Again, I want b. I don't want b squared. So somehow I gotta get rid of this exponent. I need to get rid of this squared. So what's the opposite of squaring something? That's square rooting it. So I'm going to square root the left and the right, giving me b is equal to 5. So I'm going to put that on my triangle, just so I have it labeled. So this is great. I have all 3 sides of my triangle. The next thing I'm going to go ahead and do is, just like before, I'm going to go ahead and label what's my hypotenuse, what's my opposite, what's my adjacent. So remember, I'm talking about in relation to this angle on the top right. So which side is my adjacent side? Well, adjacent should be the side that's next to theta, but not my hypotenuse. That leaves me with adjacent being A. What's my opposite? Opposite should be the side that's opposite to my angle. So here's my angle. The opposite side should be B. And then my hypotenuse is the longest side, C here. Alright, so now that I've labeled these, we've done a lot of the hard work already. I can now finally get my 6 trig functions. So let's start off with sine. Sine is, well, opposite over hypotenuse. Opposite is 5. Hypotenuse is the square root of 29. So I'm going to put 5 over the square root of 29. Now there's one thing that I need to note here. You may have seen this idea before, but often in math, we don't like having a square root on the bottom. So how do I get rid of the square root on the bottom, but still keeping essentially the same number, or an equivalent number? Well, the trick that we're going to deal with is I'm going to multiply by the square root of 29 over the square root of 29. So how does this help me not have a square root on the bottom? Well, first off, I'm definitely allowed to do this. This number that I'm multiplying here, square root of 29 over square root of 29, that's still 1. Just like how 7 over 7, that's still 1. But let's see what happens whenever I multiply across. On the top, I have 5 times square root of 29. There's not really much I can do there. But on the bottom, the square root of 29 times the square root of 29, that's actually going to give me 29 on the bottom. Why does that happen? Well, if I do square root of 29 times square root of 29, that's the same thing as saying square root of 29 squared. And we know that a square and a square root cancel each other out. Another way that you can think of this is that if I wrote 7 times 7, that's the same thing as 7 squared. So that's where we can think of the squared coming from. So by doing this, I no longer have a square root on the bottom. And that's great. So this is going to be my answer for sine. What about for cosine now? Cosine, we should now know, is adjacent over hypotenuse. So 2 divided by the square root of 29. And I run into the same problem. I don't want a square root on the bottom. So I'm going to multiply by this square root of 29 over square root of 29, and I get a very similar looking answer. On the top, I multiply across, giving me 2 square roots of 29. On the bottom, I get 29. Now for tangent. Tangent should be the opposite over the adjacent. So my opposite is 5 divided by the adjacent, 2. So 5 over 2, and I don't need to do any special multiplication because, well, I don't have a square root on the bottom, and this is already simplified all the way. So I have sine, cosine, and tangent. Now let's move on to the other three. Cosecant. Cosecant of theta, you can think of this as saying, well, this is the hypotenuse over opposite. What is my hypotenuse? Square root of 29. What's my opposite? 5. So I should be able to write this as square root of 29 over 5. Before I move on to the last two, there's one thing I want you to notice. Some of y'all might be thinking, well, last time we just flipped sine and we got cosecant. And yes, we could still do that. If I look at sine and I flip this, then I would end up with a square root on the bottom, and then I would have to rationalize again. Another way that you can think of this is that from the very beginning, this is what we originally got for sine, 5 over the square root of 29. If I flip that, I also still get square root of 29 over 5. So all of this to just say I don't want a square root on the bottom, where it may not be so obvious that these are the same thing just flipped, but we just don't want that square root on the bottom. Alright, what about secant? Well, secant, you can either think I can just flip this original version of cosine, giving me the square root of 29 over 2, or you can think secant is hypotenuse over adjacent, giving me the same answer. So there's two ways that you can always think about these on the second triple. Alright, and then cotangent. Cotangent, this should be the adjacent over opposite, or the flipped version of tangent. Either way, I get 2/5. So I have my 6 trig functions. So this is what happens if I'm missing 2 sides of my triangle, and I need a third one. I need to use my Pythagorean theorem. Alright, so that's example 2. Now let's move on from here. Last example, I believe this should be the last example. Suppose that on some right triangle, I give you that these two equations are true. Somehow I know that sine of theta is 2/3, and cosine of theta is a square root of 5 over 3. Go ahead and try to figure out what are the last 4 trig functions at my angle theta. So where do I even work from here? Right now, I don't even have a triangle drawn out. But I do have these trig function values. So what I'm going to do is I'm going to draw an arbitrary right triangle. Something like this. And I'm going to go ahead and fix my theta. So I'm calling this an arbitrary right triangle because this triangle is not going to be to scale. I don't know what my triangle looks like, but I'm just using it for the purpose of thinking about this very generally. So I chose theta to be this angle on the bottom left. Again, very arbitrarily. I could have chose this top one, or the one on the top right, but it still would have been the same. It's just that your positions might be a little bit different. So, what can I do with this triangle? How can I fill it out? I know I need all 3 sides of my triangle to get all the trig functions, but right now it looks like I have none of the 3 sides. Well, actually we do have a couple of the sides. We know that sine of theta is 2/3. Well, remember, sine is equal to the opposite over the hypotenuse. And I went ahead and labeled these, by the way. Opposite being the opposite side, adjacent being the adjacent side, hypotenuse being the hypotenuse. So, since I know that sine is opposite over hypotenuse, well, if I look at this fraction, that's giving me a hint saying, well, I can say that my opposite is 2 and my hypotenuse is 3. And I can also do the same thing for cosine. So as I said, opposite being 2, hypotenuse being 3. From my second equation, cosine, since cosine is adjacent over hypotenuse, this tells me my adjacent should be square root of 5, and my hypotenuse should be 3, which matches what I had earlier. So even though I didn't draw you a triangle from the very beginning, technically I did give you all 3 sides of the triangle already. I gave you the opposite, the hypotenuse, and the adjacent. So this one's a little bit of a hidden triangle that we're looking at. Well, now that I have all 3 sides of my triangle, I can get the remaining 4 trig functions. Let's start with tangent. Tangent, we know, is opposite over adjacent. The opposite is 2. The adjacent is the square root of 5. But I've got a problem here. Do I want a square root on the bottom? Definitely not. We don't like square roots on the bottom. So how do I get rid of the square root on the bottom? I have to rationalize, which is a fancy term for saying I multiply by square root of 5 over square root of 5. If I multiply this out, 2 times square root of 5 gives me 2 square roots of 5. Square root of 5 times square root of 5, that gives me 5. So I have tangent of my angle theta. Now I have my remaining 3 trig functions, starting off with cosecant. Well, you can either say cosecant is hypotenuse over opposite, so 3 over 2, or you can say that cosecant is the reverse, the flipped version of sine, that is 3 over 2. What about for secant? Again, we can say secant is hypotenuse over adjacent, 3 over the square root of 5, or the flipped version of cosine. But again, I don't want a square root on the bottom, so I have to rationalize, giving me 3 square roots of 5 over 5. And then my very last trig function, cotangent. Cotangent, again, you can say tangent is opposite over adjacent. So cotangent is adjacent, square root of 5, over the opposite. Or you can flip your original tangent function, as we can see here. If I flip 2 over square root of 5, I get square root of 5 over 2. So this gives me my 6 trig functions. Sine and cosine were given, and we found the remaining 4. So this is another way that we can view and find our trig functions. Alright, so that is example 3, and the last example for this section. Alright, I'll see you for the next one where we start talking about the graphs. Well, not the graphs. We start talking about more general angles. How do I deal with tangent, cotangent of some other random angle where I don't have a triangle? But besides that, I'll see you next time.